utility, maximize it, run it, cut the demand. That's the one-step optimization. In a producer theory, there's a two-step optimization. First, you find optimal allocation of factors. I will give you cost function. That is lecture number 7. Then, given the cost function, what do you do? Given the cost function, you maximize profit. I will give you a bar, so you end up with two-step optimization. Find the optimal allocation of factors that will give you the cost function, take it, and maximize profit to get the supply function. Fine, that's lecture number 8. And lecture number 6 is basically defining the production function and working with it. That's sort of the beginning setup. Alright? But it's not one-step optimization. It's two-step. Is it harder than a consumer theory or easier? It's more technical, but probably easier because the mathematics of it is similar to consumer theories. You have the same ideas, the same mathematical process. You just apply it somewhere else. That makes it easier because you're familiar with the techniques. And there is no corner solution. That makes it easier again, and there's no stuff like heat project and stuff like that. Full standard. Right? So most people find that producer theory is actually easier to work with, although I think more mechanical, more technical. Anyway, lecture number 5 is the production. The production is how the inputs become the output. We at least have 3 inputs, not 2. Although we're limited to 2, we at least have labor, capital, and intermediate goods. If you think of production, they at least have 3. You take some goods, you take some labor and capital, and turn them into something else, right? So there are normally 3 at least inputs, but if you have 3 inputs, then you cannot graph it. You end up with too many dimensions, right? So normally they put this together and call it case. So when you say labor and capital, it's basically labor and everything else. That everything else becomes capital, and capital is basically the actual physical capital plus intermediate goods that are combined. Alright? Make sense? Okay. Okay, we assume the function, the production function is efficient. That's the only assumption, in fact, we make. Unlike the consumer theory where we had at least 3 assumptions. There we assumed completeness. What's the second one? Transitivity, conservation. The first 2 were required, the third one was made to simplify. Here you have one assumption. Efficiency. We assume the inputs, the production is efficient. Which basically means no idle input. You don't have inputs just doing nothing. They must do something, right? So that's sort of obvious. If the inputs are idle doing nothing, you cannot minimize your cost. It's impossible, right? You have labor doing nothing, right? That is inefficient. Or sometimes we say Q, the outer edge, i.e. the maximum production possible with given inputs. Anything less is possible, but inefficient. So the production function characterizes the maximum possible given input and technology. Anything less, we could call it inefficient. Alright? Okay. Anyway, that is more. We assume, well, we don't assume, the production way is defined all all the numbers are flows. In the micro, the inputs are flows, the output is a flow. That's not what you have, that's how much. The inputs aren't how much input you have, they are rather how much of the input you use given a period of time. Say, a farmer uses 20 tractor hours a season, 100 labor hours a season produces this amount a season. That's the flow. The labor and capital are in terms of how much of them you use for a given period of time. So what you have is irrelevant. That's a stock of capital, stock of labor, that's irrelevant. How much are used? The period of time, that's relevant. That will give you how much you produce for that period of time. So all the numbers in production are flows, not stocks. Right? If you've taken macro, you've seen solo production function there, everything looks like a stock. That's what you have, right? That's it. Capital in the nation, that's a amount of labor there. That's not what it is in the micro. In micro is how much of it you use for a period of time. They're all flows. Make sense? Okay. We assume the labor is mobile, is not set. You can change the labor as you wish. It's not like Canada Post where you have lifetime appointment. I think that's what they're fighting on. They're fighting on lifetime appointment, right? They're on strike. The Canada Post is always on strike. They're on strike 3 times a year, right? So every time you basically want to send a mail, check whether they will be on strike next week. Because that's what happens. Every time I order something from Staples through that system, the universe system. It never arrived. Because as soon as I ordered it, they went on strike. That's just that's what happened, right? The labor there, I think that lifetime appointment. That's part of the deal. If you go there, they can't fire you. That fixes the capital. We assume that fixes the labor. We assume the labor is mobile. They can get rid of it anytime you want. So labor is never contracted. There's no union there that forces you to use it, right? You can get rid of it anytime you want. That's just an assumption. We think the labor is very hard to get rid of. Occasionally, that makes the difference between short run and long run. In the short run, some of the input is fixed. And since the labor is assumed to be completely mobile, how will be the capital? So as soon as you fix the capital, you make the production short run. And the short run becomes the time it takes you to liquidate the capital. Sometimes in 1 month, sometimes 1 week, sometimes in years. Alright? Say, if you start a business where you have to basically rent a place, you sign a contract there, that makes you short term. Until the contract expires, you're in short term. Make sense? So in that case, the capital part of it becomes leasing a place. Make sense? Okay. So we assume the capital is fixed in the short run, but it takes time to get rid of it. Alright? In the long run, no. So that is the short run. In the long run, nothing is fixed. There's no bar there. They're all they can be liquidated. Anyway, having said that, in the real world, you're never in the long run. Long run is just hypothetical. You're always in the short run. At any point in time, something is fixed. Right? The long run is just what you want to be. What if you could have changed, right? That's sort of the long run. So if you go forward and see what we do, the long run is actually non-existent. You just move from one short run to another one, to another one, to another one. Because at any point in time, the capital is fixed. Make sense? So you don't need to see the long run. The long run becomes, what if we can change the capital? That's the story. Anyway. Okay, let's start with the short run. You fix the capital, then you can change the output through changing the labor. That's the only way to do it. So the production should look like this. That's the labor, that's the output. You change the labor, you change the output. And normally, the production in the short run looks like this. Normally, that's typical. Why? Why a typical production function in short run looks like that? That is due to law of diminishing margin return. So you can cross straight line. The DMR give you that shape. That's the DMR. Diminishing margin returns, which is not required. Diminishing margin is not required. The assumption is efficiency only. This is typical. A typical short-term production function is governed by diminishing marginal return. You fix the capital. Initially, the labor is productive. More of it becomes even more productive. But at some point, it will saturate. The capital becomes less and less productive. That's typically the case. Make sense? So you have two tractors. If you have one labor, it can produce something, but not much. If you have three, it can produce more, right? Three probably can exchange time and even do better, but if you have like 10 of them, then you're not going to have enough capital to go up to default. That's DMR gives you that shape because the slope of production, that is what we call MPL. That is how much the last unit of labor produces. Initially, it produces a lot because you have a lot of capital to work with, right? But at some point in time, that will saturate, DMR sets in, and then the MPL falls. This is where DMR sets in. Then you have not enough capital, the labor won't produce as much, then productivity falls. Make sense? That's the shape of MPL, which is governed by DMR, and DMR is not required. So, no, I'm saying it many times, that's not required. The only assumption you make is efficiency, that's it. DMR is typical, not required. Now, at some point in time, MPL becomes zero. The last labor you have produces nothing. Because now you have too many labors. Because of friction, they don't produce anything, right? That is when the production thereafter becomes, what do you call it? It becomes inefficient. So efficiency mechanically means this must be more than 0. This is 0 negative. That's an idle input. It doesn't do anything either, or it hurts production. Either way, it's inefficient. So this is where we stop. Thereafter, production is not efficient, so you don't even draw it. Make sense? Okay, that is MPL. APL is average product of labor, which is Q divided by L. Alright? You want to graph APL there, how does it look like? Say that's the point. That's the amount produced. That's the amount produced. That's the labor used for it. How do you find the average product of labor there? At that point, visually speaking, what will be APL? It must be the slope of this line. That's math, right? Q divided by L is the slope of a straight line from that to that. The slope of the blue line is APL. That's geometry. Make sense? So, if you look at APL, what is happening to it? See? Oh, yeah. If you look at APL, what's happening to it? If you look at APL, see that is rising. Right. Start from very low point, rises. APL is rising. All the way to where? All the way to? I don't see. I missed it. All the way to 10. See, APL is rising, going up, all the way to this point. That is the highest APL you find. That's the highest average. But that's the tangency too. So that's the slope as well. So at that point, the average is equal to? Oh, that's always the case. Anytime the average has inflection point, at that point must be equal to the margin. That's just math, right? So anytime, any average cost, average profit, average product, anything, any average. If it has inflection point, at the inflection should be equal to margin. Make sense? That's just math. Think about this one. Suppose you don't even know what MPL, APL is. Someone asks you to maximize that one. What do? You take derivative. Right? That's what you do. If you take derivative of a ratio, how will that be? Numerator by denominator minus denominator by numerator and denominator. What do you do with that one? You forgot the rules of derivatives. Numerator, denominator, denominator, numerator, denominator squared, right? Make sense? Put that equal to 0 and solve it. You're going to end up with this. That's MPL. If you take this down there, that would be APL. So the outcome is when the margin is maximized, when the average is maximized, APL must be equal to MPL. That's just math. Anytime you maximize or minimize the average, it doesn't matter what the area is, the application is, you always equal to the margin at that point. So the margin guides the average. Think about it. Why the average is rising here? Why the average product labor is rising there? Because the last unit of labor produces more than the average, push up the average. Why the average is falling there? The last unit of labor produces less than the average, pull down the average. So margin guides the average. The average rises if the margin is higher. Falls if the average is lower. If the margin is lower, the inflection must be the same. Right? That's just math. Think about it this way. Say the average for midterm is 69. Hopefully it's more. Okay, 69. If I figure out I haven't marked a student and mark it, that student gets 75. What will happen to the average? Goes up. Make sense? 65, it goes down. If it's 69, it remains the same. The last paper I marked governs the average. Right? So in the world of economics, everything should be based on the margin. The last unit, that should be the only relevant thing. So that decides the average, right? Unfortunately, in the real world, everything is based on the average. People don't understand the margin. So if you talk to someone and say, this is the average profit, this is the average cost, this is the average event, stuff like that. Completely irrelevant. The average is decided by the margin. So everything you decide should be based on margin. So if you want to study, you shouldn't say, this is the average return to the number of hours studied. That's irrelevant. You should say, the last hour I studied, what's the return to it? Based on that, you should say. Make sense? That's the average decided by the margin. So if the average decided by the margin should be the focus. That's the way you see it when we go mechanically forward. Everything in economics based on the margin. You put marginal cost equal to marginal value, you put marginal, what else? All the marginal output equal to the margin. Marginal benefit equal to marginal expenditure, you'll see it forward. But in economics, everything is based on the margin. That's the reason. Margin guides the average. Right? Okay, anyway. Having said that, this is typical. When you work with mathematical functions, normally you don't get the whole picture. You either get this side of it, or this side. You either get the rising side of it or falling side of it. It's very hard to find a mathematical function that we use often, which will give us the whole thing. I'll show that later. Make sense? Okay. That is all the way to there. That's the short run. In the long run, nothing is fixed. That's the long run now. Nothing is fixed. Define the locus of all combinations of labor and capital. That gives you the same production. Define it as iso quant. Sort of similar to indifference curve. That was the locus of all combinations that give you the same satisfaction. This is the locus that gives you the same production. So all those combinations of inputs will give us the same production. Right? A typical I-sequence is convex smooth to the origin. A typical. There are exceptions too. I will explain why in a bit. But I-sequence can't rise. Impossible. You cannot have I-sequence that looks like this. That is impossible. Why? You can never have I-sequence that rises. Impossible. That violates some important condition. Why is it? What is it? What do you violate if you graph an I-sequence like that? There is one assumption only in the producer theory. That is efficiency. You violate efficiency. Because this labor capital produces equal to this one. So what did the extra labor and capital did? It did nothing. That's inefficient. A rising isoquant means more input doesn't do anything. It keeps you on the same indifference. I shouldn't say indifference. On the same isoquant. So that's inefficient. Make sense? You shouldn't have a rising isoquant. It's impossible. In the consumer theory, it was possible. It meant one of them is bad. Make sense? Here it's impossible because we assume inputs are efficient. They cannot be bad. They must produce something. Right? So that is impossible. We never have a rising isoquant, it's always false. And more output should be moving you to the right isoquant. This is 1, this is 2. If you move to the right on the isomap, you should get higher Q. Why? Why? If you move to the right, you get more output. What conditions violated otherwise? If Q2 is less than Q1, what do you violate? Well, there's one assumption in producer theory. That is efficiency. If you move to the north, you're using more of both. You should produce more, otherwise that's inefficient. Make sense? So, one isoquant should be downsloping because otherwise efficiency is violated. To the right you go, you should get more output, otherwise you violate efficiency. Fine? Make sense? Okay. The slope of the isoquant, ignoring the sign, is called MRTS. Similar to MRS, but you put a T there because that is margin rate of technical substitution. That is how inputs are exchanged with each other. Right? That's the reason they put technical there. You move from one technology to another one. You substitute labor and capital. You move from one technology to another. That's the technical substitution. Make sense? We'll show it later why the case, but this is MPL divided by MPK. Similar to MRS was MUX, MUY. Here you get MPL, MP. Alright? Make sense? Okay. A typical isoquant should be convex smooth to the origin. Why? Why a typical isoquant should be like the one I graphed? What's the reason for it? First, these two cannot be zero. That's our efficiency. Right? So this should run from close to zero but never zero, close to infinite, never infinite. Make sense? Because otherwise you valid efficiency. But why is not constant? Why is not like 4, 5? Why is not a number? Why is not a constant number like 4? Why don't we get a straight line? Isoquant. Why is it convex smooth to the origin? Why typically is convex smooth to the origin? Because of DMR. Although DMR is not required, but typically applies, and the application of DMR gives you convex smooth to the origin isomap. Because more labor you use, less productive it gets. Less capital you use, more productive it gets. This should fall. You move along. An isoquant, move down around the isoquant, you're using more labor, less capital. If you're using more labor, less capital, the labor should be less productive, that's the MR. The capital should be more productive, that's the MR too. This should fall. So a typical isoquant will be convex smooth divergent due to diminishing marginal time. If you have a straight line, that's valid DMR. It's possible, but DMR is not really required. It's typical. So typical isoquant is convex smooth divergent due to DMR. If you move along the isoquant, if you move this way, L is going up, MPL is going down, that's DMR. K is going down, MPK is going up, that's DMR. That means MRTS is falling. Make sense? That is the reason you get convex, smooth divergent, isomap. That basically tells you DMR holds for both inputs. Make sense? Okay. I can go beyond. Let's fix the capital and look at the slope of these two isoquants. Can you figure out the relation between these two? I fix the capital. I just use more labor. That moved me to higher production level. Make sense? I went from Q1 to Q2. What's the relation between these two MRTSs? That's one MRTS. Let's call this point A. That is MRTS at point B. What do you expect the relation between these two to be? And why? Anyone? What do you expect the relation between MRTS at point A and B to be? Knowing that MRTS is actually this ratio. MRTS tells you how productive the labor is relative to capital. That's what it says. It's a ratio of MPL. The high MRTS means labor is really productive. Low means not so much. So what's the relation between MRTS 1 and MRTS B? Which one is higher, which one is lower, or they're probably equal? What do you expect the relation to be? This should be higher than this, due to, again, the MR. At point A, you use less labor versus point B. The capital is the same. See, the capital is the same. You just use more labor. If you use more labor, the productivity labor should fall. That's the MR. So you should expect not only falling MRTS across one isoquant, but if you go to more than one isoquant, you should fall too, if the MR holds. And the MR is not required. It's typical. Make sense? So, MRTS falls across one isoquant, that's typical. And if you go to more than one isoquant by keeping the capital constant, it should fall too, if the MR holds. Alright? Okay. Okay, let me give you a numerical one. See if it makes sense. That's one isoquant, that's two, that's three. I kept the capital constant. Say 5. Right? This is 1, this is 2, this is 3. The capital is 5. I use 1 labor, then 2 labor, then 3 labels. That pushed me up across 3 different isoquants. This is Q1. This is Q2. This is Q3. I don't know what Q3 is. Make sense? I don't know what Q3 is. What would be Q3 range? What's the range of Q3? Such that 1, labor is efficient. See, I know I should put a U there, a Canadian labor, right? But it's not efficient. I did not put a U. I don't know what can even have like U in the labor, right? That's like a waste of ink. Anyway, it's not very efficient. And it doesn't do anything. It's inefficient. Anyway, we want the labor to be efficient. That's one. Two, we want DMR to hold for labor. What would be Q3? What do you think Q3 should be? If you want both of those two to hold. The first one is required. The second one is not. But I assume it here. I assume DMR holds for the labor. What would be the range for Q3? Anyone? Start with efficiency. If you want the labor to be efficient, what should be the minimum value for Q3? How much? What's the minimum number for, what's the minimum production for Q3 such that the labor is efficient? Well, this labor should produce something, right? It should produce something. That should tell you Q3. What's the range for Q3? It should be more than? Yep. More than 100. Because this labor, the first labor went from 50 to 100. That third one should push you up. It cannot be less than 100. It's inefficient. Even if it's 100, it's efficient. It has to be more than 100. That's that. Make sense? So the lower end of the range should be 100, otherwise the labor is inefficient. It produces nothing or it produces negative number. Right? What about DMR? DMR should give you the upper end of the range. How do you verify DMR? DMR said more labor, less MPL. It beats the second derivative. But here, you can actually find the MPL and verify them. What's the MPL of second labor? That's second labor, how much produces? Well, let's see. That is 100 minus 50, that is 2 minus 1, that is how much the second labor produces, which is 50. Right? Second labor produces 50 units. That is MPL of 1, 2, 3. What's the MPL of 2 to 3? That should be Q3 minus 100. 3 minus 2, that is unknown. But the question said DMR holds. If DMR holds, what should that number be? It should be less than how much? 50. The third labor should produce it less than the second one. If diminishing margin terms holds there. Alright? So that will give you the range for Q3. The Q3 must be less than how much? 150. If the Q3 is within that range, then you have the labor efficient and DMR hold. Alright? As I said, this is a must. This is the must. The other one is not a must. DMR does not have to hold. It's not required at all. It's typical. Alright? Make sense? Okay? Okay, anyway. If it makes sense, perfect. If it didn't, you're going to see it on your quiz. It would make sense then. But the idea is simple, right? The labor should be efficient. If DMR holds, that give you the upper end, because any more that'll make it more than what the first labor produces. Right? Okay. Okay, we are done with this one. Functions. We use two classes of functions. In the consumer theory, we use three. Convex smooth to the origin, that's number one. Special cases, perfect complement substitute. And number three was, what was number three? In the consumer theory, there were three classes of functions. Number three was quasi-linear. Here, there is no quasi-linear. Quasi-linear technically valid efficiency. You don't have it, right? That's gone. No quasi-linear exists in the producer theory. Let's simplify the whole thing. We have the first group, convex smooth to the origin, and that group is called Douglas. That is the production. Make sense? What's the MRTS for it? What's What's the MRTS for it? Anyone? What's the MRTS for this? It's the same thing, the same rule of thumb as in consumer theory. You just K replaces Y, L replaces X. The rest is the same. Make sense? So what's the formula for MRTS? Alpha, beta, K, L. That's MRTS. Make sense? What's the MPL for this function? That's the MPL. That's the MPL. Make sense? Can MPL be negative? Can it be 0? No, this is always more than 0. So labor is always efficient. Labor is always efficient. You don't have to worry about, well, this is inefficient, I have to fix it, right? The Cobb-Douglas give you always efficient labors. NPL, then NPK will always be more than 0. That's NPL, NPK should look like this. All these obviously we assume alpha, beta, A, they're all more than 0. Otherwise that's not Cobb-Douglas, something else. So Cobb-Douglas gives you always efficient factors. You don't have to worry about trying to find out where the labor and capital become inefficient. They're always efficient. Alright? What about diminishing margin returns? Do you think diminishing margin returns always hold or it depends? Look at MPL and then MPK and tell me what about diminishing margin returns? Efficiency always holds for both MPLs, for L and K. What about diminishing margin returns? Would it hold? Yes or no? DMR is basically the second derivative. If you take the second derivative, if it's negative, DMR holds. Make sense? So by looking at these two, what's your conclusion? See, that is determining the sign. If you take second derivative, this becomes multiplied there. Right? This determines DMR. If alpha is less than 1, DMR holds. If alpha is less than 1, and beta is less than 1, DMR holds for both inputs. That's the condition. If you use Cobb-Douglas, you don't have to worry about efficiency. Inputs are always efficient. Right? But to get DMR, alpha and beta both have to be less than 1. Otherwise, the second derivative becomes negative. Sorry, become positive. Then more labor produces even more than the one before. Make sense? Okay. Anyway, that's the reason when you see us using Cobb-Douglas, we always make sure the power is less than 1. Alpha and beta less than 1. Otherwise, DMR is not going to hold. Make sense? Okay. The second function we use is CES, which is this one. What's the MRTS for this one? What's the MRTS for CES? It's the same shortcut as before. K, L, what's the power? 1 minus? Oh. This sort of more or less like Cobb-Douglas, right? Efficient, the inputs are always efficient. They're always efficient, right? DMR holds as long as alpha is less than 1. Okay. Anyway, we use these two often. These two are the ones that use often. We'll see some of them soon. But there are unconventional production functions. Unconventional production functions should satisfy efficiency, but won't satisfy necessarily DMR. And the main one is, this is group 2. The main one is fixed proportion production function. That is sort of function that is not the standard one, DMR doesn't hold there. That is the way we write it. Often it's called the Leontief function as well. So either one is fine. Don't call it perfect complement as you call it in the consumer theory. As soon as you say perfect complement, they're talking about consumer theory. In the producer theory, they call it fixed proportion production function or Leontief production function. Make sense? That production means the inputs are used in this combination. Anything outside that combination does not produce anything. So anything outside that is inefficient. And since we assume production is efficient, we're going to stay on that line. Make sense? Say, Uber driver. They must have one car and one driver. So what's the alpha and beta there? 1, 1. Makes sense? One car, one driver. So production must be on this line. That's the only efficient production. That's the only efficient production. That's K. That's L. Anything else on that line is inefficient. Right? Suppose there's a driver, one driver. They need one car. Make sense? How much would they produce? How much do they produce? This is 1, this is 1. They're going to produce 1. That is 1. Make sense? Suppose now there are 2 drivers and just 1 car. How much that produces? 1. So that extra labor didn't do anything. It kept you on the same in the same isoquant. As a result, you will end up with what you had before in L-shaped isoquant. Basically means if you depart from that line, more capital, more labor, it doesn't do anything. So technically, the wings, this wing, these are all inefficient productions. Because you have labor doing nothing. You have drivers sitting idle, right? Those are cars sitting idle doing nothing, but you never go on the wings. You stay always there. The rest of the isoquant is never used because we assume production is efficient. Make sense? Okay. Question for you. What's the MRTS down here? What's the MRTS on the horizontal part of the isoquant? How much? 0. What does 0 mean? 0 means MPL is 0. That's the meaning of it. It means the labor is inefficient. But you never go there. What about MRTS up here? That is, how much? Infinite. Which means MPK is 0. So on the wings, either labor or capital is inefficient. So you never go there. You never go there. You just stay on this line. It's the only efficient production. If you have 2 drivers, you'll be forced to buy 2 cars, and that moves you up to higher isoquant. Make sense? If you have 2 drivers and 1 car, you have to either get rid of the driver or buy 1 car. Because otherwise the production becomes inefficient. You have labor that's doing nothing. Make sense? Okay. Anyway. You know, Uber drivers are being replaced with Waymo. Is it Waymo? What do you call it? Waymo? The auto taxis. In US they call them Waymo, right? I don't think I've arrived yet. You know why they call it Waymo? Because if you actually take it, you have to pay way more. And I think it's twice the price. I don't know why anyone wants to. It's completely idiotic. Just get someone, drive you there, rather than machine driving. The machine is much slower. The humans go crazy, right? And then you pay half the price. You have all this excitement of driving crazy in the streets, and then you pay half the price. Why do you get Waymo? I think people are just like, let's see what the machine does, right? But why? I've seen the numbers. Waymo is twice the price of an Uber driver, right? and it goes half the speed. Right? Anyway. Okay, that is sort of the setup. I left out this one. I left out this one intentionally. We come back to it next week. Unfortunately or fortunately, when you get the quiz, the first question has part of it that requires that one. Leave that one. So on the first question of the quiz, don't answer the question related to return to scale. You answer the other part of it. Right? You'll see it when it comes to it, because that one is not being covered until after the midterm. I'll do one question from lecture 5. That's for the midterm. Should look very familiar. We don't invent anything, we just repeat what we did. Different numbers, different function. But should look very familiar. Let's see. This individual is characterized by natural log function. Natural log give you risk-averse individual. We know that from last lecture, right? So it's a risk-averse individual. Risk-averse individual, the function for it should look like this graphically. That is income. That's the utility of it. So he has either 25,000 or 50,000. I need the utility of these two. So I need I want to calculate the utility of these two. Put 25,000 in the utility function. That is 4i. Take the natural log of it. What's the natural log of 4 multiplied by 25,000? Natural log of 100,000. How much is that? Anyone? Round 3 digits, as we had in the last lecture. Rounding is important when you work with natural log. With other functions, it's not really important. But if this was an exam, I would have said 3 digits. What do you get? What's the natural log of 100,000? 3 digits rounding. 11 point? I remember the 11, I don't remember the rest. The 11?
513.
513. What about 50,000? Is it 12? 12 point? That is ln 200,000. How much do you get? Yeah?
12.206.
12.06?
206.
Okay, we got those. So now we need the expected income and then the expected utility. That's the expected income. What do you got? I need the expected income, then I need the expected utility. So get me that number, then get me this one. What's the expected income? What's the expected utility? Expected income, I think it's 42,500. That I can figure it out. But what about the expected utility? Is 11 pounds? The first one's so obvious. The second one, I know the 11. 11.8. And how much? I know the 8, I think. Is it or not? Is it 11.8 or 9? And the rest? What's the average utility? 9? 9 and how much? 9. That's it? What's the third digit? 9. That's that one. We need the utility of expected income, which is ln 4 multiplied by 42,500. How much is that one? That should be harder than 11.998. So these risk averse prefer certainty over uncertainty. So you should get a bigger number than 11.998. 12 and how much? 12 pound? What do you got there? 12 pound? What? 044. That's that. And the last number we need is take the expected utility and from it get the certainty equivalent. So get the expected utility. Go to the utility function, find certainty equivalent, which is an amount that yield the same satisfaction as expected. So here, to get the C, I need to exponentiate the expected utility and divide by 4. That's the certainty equivalent, which should be lower than expected income because the individual does not like risk. It should be lower than 40,000. How much do you get? What is the certainty equivalent?
It's 40607.
40607 like this?
Yeah, 0.4.
No, it's rounded. It's fine.
Oh, okay, that's
The rounding is fine. The only one that's not fine is the natural log function. Everything else is fine. And the reason is this exponentiation will blow up the number, right? So if you have too much rounding there, that C will be wrong. That's the only reason. The only reason we care about rounding here is because of CE. Okay, connect the gamble. I did. Write the expected income. And run it through vertically. That is our utility of expected, which was how much? 12 pounds, 444, and that was expected utility, which is 11 pounds. 998. And from the expected utility, we went down there and calculated certainty equivalent, which was 40607. We completed part A of this question. We graphed everything. Right? Make sense? This area was called what? What did we call this area? This distance. We called it Markowitz premium. So the Markowitz premium is this one. That's the Markowitz premium, which basically means technically that's the money you have. That's the average money you have, but you give it up for this. Because for you it's the same equal to this. In the process you lose. That difference is the maximum you're willing to give up. So the risk premium, as defined by Markowitz, assumes if someone gives you this, for someone something that's worth this, you're willing to pay the difference. As a result, that's not risk premium for full insurance, because if you buy full insurance, you're not going to get the expected income. You're going to get 50,000. So we call that Markowitz premium. The full insurance risk premium becomes this one. So don't use that one to answer B. B is full insurance. That's the not full insurance premium, that is expected income insurance premium. Make sense? Okay. Like saying, I have this in my pocket and someone offers me this. I want to pay the difference. That's sort of Markowitz premium. Or if you reverse it, you say, my income in reality is worth this. That's in reality. But to me, it's worth this because I don't like the risk of it, right? So I'm willing to exchange what I have, which carries risk, with what risk being equivalent is. In the process, I'm going to lose that one. It's the same idea. But in the Markowitz premium, the assumption is that is what you have. If you buy full insurance, you're going to end up with 50,000. So you have to replace it with that to get the full insurance premium. B, the maximum you are willing to pay to avoid risk is, one more time. The maximum you are willing to pay for full insurance is, Markovitz, full insurance premium. That's a pie. I should say. In the world of economics, pi is premium. That's the way they know. Everywhere you see pi is a premium. That's sort of the tradition, right? Sometimes they put R, sometimes they don't. But anytime you see pi, that's sort of a standard for premium. That's the way they have it. I don't know who started it, but that's a tradition. That is 50,000 minus 4067, which should be 93,093 bucks. The maximum you're willing to pay to avoid, the maximum you're willing to pay for full insurance is 93,093 bucks. Right? Make sense? Okay. That's part B. Part C. Partial insurance. The question says you have 20,000 in coverage for 10,000 in premium. Would you do it? Now the question gives you dollar coverage. What if this was percentage coverage? How much would have been the percentage? Normally we don't give you dollar coverage, we give you percentage coverage. If this was percentage, what would have been the percentage? You would have said that's the loss. That is the loss. And that is percentage of the loss. We should find it. That should give me 20,000 coverage. So that would be 80%. So the way it was initially, we're at 80% coverage, but in dollar terms, that becomes 20,000 bucks. You're covered on the loss. The loss of 25,000 here, and 80% of it is $20,000. Right? So I could have said there is 10,000 premium for 80% coverage. Would you do it? That would be actually better. Right? Okay. Anyway, again, for partial coverage, you should do expected utility approach because you already have expected utility of no insurance. How much is that? 11.998. You just have to find the expected satisfaction you get from buying the insurance. Right? And that's not very hard to do because that is the money you have on your own. That is the probability of it. If you buy insurance, there is no coverage there, and you get 20,000 in coverage there. But you have to pay the premium either way. So you end up with 40,000 there and 35,000 there. You just have to find expected satisfaction of that stream of income, which should be 30% of LN 4 multiplied by 35,000 plus 70% of LN 4 multiplied by 40,000. I need the whole thing, but give me these two numbers individually as well. I need these two as well, but I need the whole thing to make a decision. What's the satisfaction of 35,000? What is ln 4 multiplied by 35,000? 11 point? 11 point? How much is that? I need the individual numbers because we use it later. 849? What's the other one? That looks like 12 or close to it. 983? So what's the whole thing? Where's the expected value there? 11 point? 11 point? How much? 11.9 I remember the 9. 9?
943.
Huh? 4-3? 4-3, that's not a good policy. Not a good policy. You can say too high a premium or too low a coverage. Either way, not a good policy. You're not gonna do it. Yep.
Sorry, I just have a question. On the point 3, how do you get 35,000?
That is 35,000.
Yeah, how do you get that one?
Well, you have 25,000 on your own, right? This is what you have. That's a 20,000 coverage. The insurance company, in the case of loss, pays you 20,000 bucks. And then you have 10,000 bucks paid in the premium. So it'll be 45 minus 1035. Like that? This is basically a premium coverage. This is the coverage by the insurance company. That's what they give you. This is what you pay. So you end up with 35,000. So another good policy, too little coverage or too high a premium, either way, not a good policy. What make it more enticing if the probability of loss was higher or lower? Because now you don't do it. If the probability goes up, will that make it better or worse? Will it make it better or worse? With 30%, you're not going to do it. If it goes up, the probability, will it make it more likely to do it or less? More or less. The higher probability of loss, the better the insurance policy would be. So 30% is not good enough, but if it goes up at some point, you may say, well, that's good. The next part is fine. The break-even point, fine. Probability of loss, call it P, such that you are indifferent. Indifferent. Between buying a 20,000 coverage and not. So we're going to find the probability. We know it's more than 30%. We know it's more than 30%, but with 30% you didn't do it. Fine? So I have to find it. Question for you before I set it up and solve it. Do you think it's much higher than 30% or close to 30%? We know it's higher. But is it much higher, like 60 to 70%, or not much higher? What do you expect it to be? Do you expect it to be much higher or close to 30%? Anyone? Wow, look at these two numbers. So not far off, right? So it should be higher, but not much. If they were really far off, then really the probability to be higher, right? But based on those two numbers, my guess is not too much higher. It's higher, but not like 40, 50% higher. It's a bit higher. Let's see. So form expectation, then if you make an error, you figure it out. That is expected utility without the insurance. That's the probability which we have to find. That is what you end up with. And that's the probability of no loss. That is what you end up with. We do have these two numbers already. It's on the graph. How much were they? That was 11.305. Help me out. Was it 305? 503? Oh, 513. 513, 206. Make sense? There's that. And expected utility width as a function of probability will be this one. And that's the reason I asked you for those two numbers, because we need them here. We need them there. Right? Okay, now we have to arrange and solve. I put the probability one side, 1 minus the other side, and try to solve it. So I need now this minus this. How much is that? That is the probability side. 11.849 minus 11.513. That's 336? That looks like 336, right? Like this. What about the other one? Now I need this minus this. That's 206, that's 0.017, that's 223. 223? 223. So the probability should be 0.223 plus 0.336. I know it's more than 30%, but not too much higher because the numbers were so close. What do you get there? It's more than 30%. Definitely, but not much. What do you get? It's less than 40% probably.
It's just about 40%,
About 40%?
like 39.8.
Like this? Yeah. It's more than 30%, but not that much. Because we know that before, the numbers were so close, right? It's hard to say because natural law is very hard to say. It's not really the number, right? But they were close. You can guess. It can't be so far, right? Makes sense. So form expectation because if you solve it, you will notice if you get an error. Alright? Make sense? Okay. That is lecture 5. I did post a sample questions, right? Did I? I did, right? Did I post sample midterm? I think I did. If you check it out, you see a question like this there, or a different variant of it. How many points it have? 15? That's a lot of points, right? These are 15 points. If you know it, no problem, in 5 minutes, 10 minutes, done. If you don't know it, well, you should know it. But if you make an error there, that's unforced error, right? So you know it's coming. Make sense? And you know, it's sort of very limited topic, limited stuff you can do from. Right? So practice it. Practice it, make sure you don't make an error. I've seen people having problem with a graph, right? The graph is not just random, right? Connect the gamble, identify it, and everything will go through it. But when you look at the graph, you should know what is going on. Because if you know it, then you become the different version of it. Otherwise, it will be messy. You're gonna mix up. I've seen it many, many times. Anyway, lecture number 6. I made a production function here just to see what will happen. Does this production function, any part of it look familiar? Does any part of this production function look familiar? Yes or no? What part looks familiar? This part should look very familiar. What is that part? If I write it this way, does it look familiar now? Yes or no? That is, the first part of it is Cobb-Douglas. This is Cobb-Douglas. That's a Cobb-Douglas. It's just written as a square root instead of power, so it doesn't look like it. I took Cobb-Douglas, added subtracted. If I would not have added subtracted, we already know the outcome. It would have been convex smooth to the origin, the isoquant. The labor and capital will always be efficient, and DM1 would hold because the power is less than 1. But I changed it. So let's see what happens now. What is MPL? MPRA is this one. What is MPK? MPK is this one. Two questions. Are the input always efficient? Yes or no? Start with the capital. Is the capital always efficient? Yes or no? Efficient means this must be more than 0. Is this always more than 0? Yes or no? It's all, well, so of course always more than 0. This cannot be negative. This cannot be negative. That's the plus. This is always more than 0. So the capital is K is always efficient. It doesn't matter how much capital you use, it will always produce something. What about the labor? Is the labor always efficient? No, it will only be efficient if this is more than 0. So labor is not always efficient. If you use too much of it, it will become inefficient. Labor is not always efficient because too much of it will make that negative. Alright? So we'll talk about it in a bit, but that's the first. What about DMR? Does DMR hold with regard to these two inputs? Yes or no? DMR is how MPL moves. Alright? If you wish, you can take second derivatives, but you don't have to. See, if you increase L, what happens to MPL? False. The power is negative. That's DMR. If you increase K, what happens to this one? It falls. So DMR holds with regard to both. As long as the power is less than 1, we already established that. DMR holds. It's less than 1. I know before solving it. DMR holds because the second derivative becomes negative. Nobody home. I think there's fire. Should we leave? No, it's fine. If there's a fire, we stay here and we sue them. DMR holds. I don't think there's fire. You know when they constructed this building, like 2010, there was a fire, not fire, someone plugged these things. You know what happened? The system was built to lock all the doors. So this fire, all the doors are locked. That's not very smart, right? When they came back, fixed it later. Anyway. Okay. Now let's go to the first one. The labor is not always efficient. Say, suppose you use 100 capital. Suppose you started to use 100 capital. Make sense? Then MPL at that level of capital will be this. This must be more than 0. That limits the labor then. If you decide to use 100 capital, that must be more than 0. That gives you the maximum labor you can use. If you solve it, what do you get? This will be 20, is it? Alright? That's 20. So you're going to get 20 divided by 12, L L less than? Yes. You cannot use more than this labor because that makes it be a negative. That's the maximum number of labor you can use. Make sense? So if you end up with a production that is not always efficient, you have to identify the inefficient side and cross it out. You can say, well, if you use 100 capital, you cannot use more than that in labor, because after the labor will produce negative number. Alright? Make sense? That's what I did. I just put this inequality and I solve for L. That tells me the maximum labor I can use. Alright? So, anyway, we'll have more of it in a bit, but production must be efficient. That's a must. There's no exception there. That's the only assumption. So if you have production, check whether efficiency holds or not. If it's not, if it doesn't hold, eliminate the part. Right? Okay. Okay, let's take a short break. Have a look at that graph. We'll do it after the break.